Last night, a B-2 Spirit stealth bomber turned back 500 kilometers from Iranian airspace. The mission was critical. The target was a heavily fortified underground uranium enrichment facility that conventional weapons could not reach. The B-2 was carrying two GBU-57 Massive Ordnance Penetrators, each weighing 30,000 pounds and capable of destroying targets buried 60 meters below the surface. It was the only aircraft in the US inventory capable of delivering those weapons to that target, but the mission never happened. Because 500 kilometers from the Iranian border, the pilot received an alert that would change the calculus of modern air warfare. His aircraft had been detected, not by visual observation, not by infrared signature, by a radar system operating on principles that rendered stealth technology irrelevant. The B-2 Spirit was designed in the 1980s to penetrate Soviet air defenses using a combination of low observable technologies. Radar-absorbent materials coat the airframe. Faceted surfaces deflect electromagnetic waves away from the transmitter. Engine exhausts are shielded to reduce infrared signature. The aircraft's radar cross-section is approximately 0.1 square meters, roughly equivalent to a large bird. Conventional radars operating in the X-band frequency cannot maintain a track on such a small target at operationally useful ranges. For 3 decades, this technology worked. B-2s flew missions over the Balkans, Iraq, Afghanistan, and Libya without being effectively targeted by enemy air defenses. The aircraft remained invisible to tracking radars, allowing it to penetrate contested airspace and strike high-value targets with impunity. The stealth advantage was so significant that the United States built only 20 B-2s, each costing $2.2 billion, confident that the technology would ensure their survivability. Then Iran acquired quantum radar. The system, designated JY-27A, was developed by China and first publicly demonstrated in 2019. Unlike conventional radar, which detects objects by transmitting electromagnetic waves and measuring their reflection, quantum radar uses entangled photons. 2 photons are quantum entangled, meaning their states are linked regardless of distance. One photon is transmitted toward the target, the other is kept at the receiver. When the transmitted photon interacts with an object, the interaction is instantly reflected in the state of the entangled photon at the receiver, even if the transmitted photon is absorbed or scattered. Stealth technology is designed to absorb or deflect electromagnetic waves, preventing them from returning to the radar receiver. But quantum entanglement does not rely on reflected waves. The entangled photon pair provides detection information through quantum state correlation, not classical reflection. Radar-absorbent materials and angular shaping, which are highly effective against conventional radar, have no impact on quantum detection. Iran purchased 4 JY-27A systems from China in 2023. The systems were deployed around critical infrastructure: nuclear facilities, command centers, and missile production sites. Each system has an effective detection range of approximately 500 kilometers against low observable targets. When operational, the network provides overlapping coverage across much of Iranian airspace. The B-2 mission planners were aware that Iran had acquired advanced radar systems, but intelligence assessments suggested that the JY-27A was still in testing and not yet fully operational. The flight plan routed the bomber through what was believed to be a gap in coverage. The aircraft would approach from the east, flying at high altitude to conserve fuel, then descend for the terminal approach to the target. At 500 kilometers from the border, the bomber's radar warning receiver activated. The system detected S-band emissions consistent with fire control radar. The pilot checked his instruments. The aircraft was at 45,000 feet, well within the range of long-range surface-to-air missiles. If Iranian air defenses had locked onto his position, continuing the mission would place the aircraft and crew at unacceptable risk. Standard procedure in such situations is to verify the threat. Electronic warfare officers aboard airborne command posts analyzed the emissions. The radar tracking was stable and consistent. The B-2 was being painted by a system powerful enough to guide interceptors to engagement range. The mission commander made the call: abort and return to base. The bomber turned west and climbed to maximum altitude, increasing distance from the threat as rapidly as possible. No missiles were launched. No interception was attempted. Iran had achieved its objective without firing a shot. The most advanced stealth bomber in the world had been turned back by a radar system it could not evade. Debriefing sessions began immediately upon the aircraft's return. Intelligence teams reviewed the radar emissions data. Satellite imagery was analyzed to identify the location of the tracking system. Within hours, confirmation came through. The radar signature matched the JY-27A quantum system. Iran had not only purchased the technology but had successfully integrated it into their air defense network and operated it in a real-world scenario. The implications were severe. The B-2 fleet consists of only 20 aircraft. Each one is a strategic asset designed to deliver nuclear or conventional payloads against heavily defended targets. Losing even one bomber would be a strategic and political disaster. If quantum radar could reliably detect B-2s at 500 kilometers, the aircraft could no longer operate in contested airspace without prohibitive risk. The entire strategic rationale for the B-2 program was predicated on stealth. The aircraft is subsonic, with a maximum speed of Mach 0.95. It has limited maneuverability due to its large size and heavy weight. Its defensive systems are minimal. If detected, it becomes a slow-moving, non-maneuverable target for modern surface-to-air missiles or interceptor aircraft. The value of the platform exists only if it remains undetected. Conventional air defense systems, even advanced ones like the Russian S-400, struggle to track stealth aircraft at long range. The B-2's low radar cross-section allows it to close within striking distance before enemy radars can achieve a reliable track. But quantum radar eliminates that advantage entirely. Detection occurs at the same range regardless of the target's radar cross-section. A B-2 appears on quantum radar with the same clarity as a non-stealthy bomber from the 1950s. Alternative mission profiles were considered. Could the bomber approach at extremely low altitude, using terrain masking to evade detection? Theoretically possible, but flying a large strategic bomber at low altitude over mountainous terrain significantly increases risk and reduces range. Could electronic warfare assets jam the quantum radar? Unknown. The physics of quantum entanglement suggests that traditional jamming techniques which work by overwhelming receivers with noise would be ineffective. The entangled photon correlation is a quantum phenomenon, not a classical signal that can be disrupted with electromagnetic interference. Could the mission be reassigned to other platforms? Cruise missiles lack the payload capacity to carry GBU-57 penetrators. Fighter bombers like the F-15E could carry smaller bunker-busting munitions, but those weapons cannot reach targets buried as deeply as the Iranian enrichment facility. The B-2 was selected for this mission because it was the only platform capable of delivering the required ordnance. Without the B-2, the target remains invulnerable to conventional attack. Strategic planners faced an uncomfortable reality. A key component of US military power projection had been neutralized by a technology that cost a fraction of the stealth program's development budget. The B-2 program cost $44 billion over its development lifecycle. The JY-27A systems purchased by Iran cost an estimated $200 million total. A $44 billion capability defeated by a $200 million countermeasure. China, which developed the quantum radar, was watching closely. The same technology could be deployed to protect Chinese airspace in the event of a conflict over Taiwan. US war plans for such a contingency rely heavily on stealth aircraft, including B-2s, B-21s, F-22s and F-35s. If quantum radar can detect all of these platforms at operationally significant ranges, the entire stealth fleet loses its primary advantage. The B-21 Raider, the next-generation stealth bomber currently in development, incorporates design features intended to counter quantum radar. The specifics are classified, but informed speculation suggests active countermeasures, including quantum-based sensors to detect entangled photon emissions and technologies to disrupt the entanglement process. The first B-21s are scheduled for delivery in 2025 or 2026, with full operational capability expected several years later. Until then, the existing B-2 fleet remains vulnerable. Russia is also developing quantum radar technology, independently of China but along similar theoretical lines. If deployed operationally, Russian quantum systems would pose the same threat to US stealth aircraft operating in European or Arctic airspace. North Korea has expressed interest in acquiring the technology from China, though no confirmed sales have been reported. Proliferation is a concern. Within a decade, quantum radar could become widely available to any nation with the resources to purchase it. The US intelligence community is now tasked with identifying every quantum radar installation globally. Satellite reconnaissance is being retasked. Human intelligence assets are being directed to gather information on production facilities, deployment schedules, and operational capabilities. But even perfect intelligence does not solve the fundamental problem. Knowing where the radars are located does not restore the stealth advantage. It only allows mission planners to avoid those areas, which in many cases means avoiding the targets that matter most. Investments in countermeasures are accelerating. Research into quantum jamming, stealth coatings effective against quantum detection, and alternative penetration strategies is being funded at levels not seen since the height of the Cold War. But technology development takes time. Even with unlimited funding, fielding operational countermeasures will require years of research, testing, and integration. In the near term, the US military must adapt to an environment where stealth is no longer a reliable advantage. Mission planning will change. Aircraft will operate at greater standoff distances. More reliance will be placed on long-range cruise missiles, unmanned systems, and cyber capabilities. The role of manned bombers in penetrating advanced air defenses is being re-evaluated. The B-2 that turned back last night will fly again. Training missions will continue. The aircraft will remain on alert, ready to execute nuclear deterrence missions if called upon. But deep penetration strikes against targets defended by quantum radar are no longer feasible without accepting losses that the US cannot sustain. Iran demonstrated that it possesses the capability to detect and track the most advanced stealth bomber on Earth. The bomber turned back, the mission was aborted, and the target remains intact. The message was clear. Stealth, the technology that defined US air superiority for 3 decades, is no longer invisible. And the balance of air power has shifted in ways that will take years, perhaps decades, to fully understand and counter. The age of stealth dominance is over. The age of quantum detection has begun.